anytime you're being asked to find a probability, you'll use normal CDF. Okay? So just keep that in mind with those two functions. I'm not going to say too much about this right now. So this is kind of explaining what MyStatLab is doing. So we will encounter z-scores again. So the purpose of z-scores for us so far has been that they help us to kind of understand how typical or atypical is a data point. So where these will come up again is there's a special normal distribution called the standard normal. So where this arises is if you have a measurement that follows a normal distribution, say like the previous example with those exam scores. If you converted that entire distribution into z-scores, so you took every exam score and found its z-score, then all of the z-scores follow a normal distribution. So if your data follow a normal distribution, then the z-scores follow a normal distribution. The probability distribution of z-scores is called the standard normal, and it has special properties in the sense that the mean is 0 and the standard deviation is 1. This is really easy to work with, and as a result, this is why you have those z-tables. So like the standard normal table that MyStatLab suggests. This distribution is easy to work with tables. This is the old way of solving these problems. Again, I'm not going to show you that. So any MyStatLab problem that offers you the z-table, you can solve using the calculator, using normal CDF or the inverse normal. Okay. Something else to keep in mind, thinking about the big picture of statistics here. In the big picture, remember, the goal is that we have some parameter that's unknown. Some true mean, some true standard deviation, whatever. These normal distributions we're dealing with use those unknown parameters, mu and sigma. But for now, we know what they are. So we're kind of taking baby steps. We're learning how to use a normal distribution, and as we proceed, we will gradually take away knowledge of the parameters and build up to our ultimate goal of, if we just have data, how can we estimate these parameters if they're unknown? But for now, we will know the parameters. So let's do another example. So to be a member of Mensa, which is like a group of smart people that, I don't know what they do, smart people stuff, I guess. Your IQ score has to be at or above the 98th percentile. Pretty high, I guess. Suppose that IQ scores are approximately normally distributed, so that's nice to know, with a mean of 100 and a standard deviation of 16. We want to know what IQ score is the 98th percentile. Well, we know that we're dealing with a normal distribution, so let's sketch that out. Something like that. This is the distribution of our random variable x, and what we're measuring here are the IQ scores. So we're told that the shape is normal, we're told that the mean is 100, and the standard deviation is 16. So we can go up and down 3 standard deviations and indicate what those are. So we have 116, 132, 148, then we have 84, let's see, 74 be 68, and then 52. I think those are right. Yeah. Just double checking. So again, by the empirical rule, this says nearly all IQ scores will be between 52 and 148. And I think that this is roughly true to reality. So when these I think they were psychologists, when they designed these IQ tests, they designed it such that the scores would follow a normal distribution. So what we want to know is which score is at the 98th percentile. And here's where that nuance comes in. What are we being asked to find? We're not being asked to find a probability. We know the probability. 98% of the data are at or below some score. So we're being asked to find a value of the random variable. We need an IQ score. And what we know about it is that it's the 98th percentile. So where is the 98th percentile? I don't know. But that means that 98% of IQ scores are below this unknown score. So that means it must be a high IQ score. And we'll just stick it here for right now. If this isn't exactly where it lives, that's okay. What we know is that it's just a high score, and we know that at or below that unknown score, this shaded region, that's 98% of the distribution. So in other words, only 2% of scores are higher. So now the task is, how do we find this score if we are given a probability? So again, what this represents is this is kind of an inverted problem. We're not finding a probability, we were given a probability, and instead we're trying to find a random variable value. So this is where that other function comes in. This is a case for the inverse normal. So we're going to find a value of the random variable. So it has a similar input to the normal CDF, but it's maybe a little more particular. So to get there, it's with all of the other distributions. So you'll press second vars, and it's just below normal CDF. So you select it, and it requires 3 inputs. And the first one is what's particular. So the first value we tell this function is what's the probability to the left of the point we're trying to find. How much of the distribution falls to the left side? So in our example, inverse normal will give us this point, but the calculator function wants to know how much of the distribution is to the left of the point. And this is nice for us because that's how a percentile is defined. How much is to the left? So in this case, we have 98% to the left. The second thing we have to tell this function is what's the mean of the normal distribution that we're working with, and then lastly, what's the standard deviation. So, to find x, we're going to use the inverse normal function. So we're going to tell it that 98% of the distribution is to the left. You have to input that as a proportion, as a decimal. The mean of this distribution is 100, and the standard deviation was 16. Okay. So we have 98% to the left, comma, a mean of 100, comma, and a standard deviation of 16. So you press enter, so that we get an IQ score of 132.86, we'll call it. Okay. And just maybe because I've done this problem before, but where we guessed this point lived is actually pretty close. It's a little bit above 132. Okay. So what IQ score is the 98th percentile? An IQ score of 132.86 is the 98th percentile. So if your IQ is above that, then you can join Mensa. So next, how many standard deviations away from the mean is the 98th percentile? So since our sketch worked out, we can see that it's a little bit above 2 standard deviations above the mean. But how can we actually find the number of standard deviations? Well, that's our old friend, the z-score. It tells us how many standard deviations away from the mean is a given data point. So we're going to take our IQ score, 132.86, subtract the mean of 100, and divide that by the standard deviation of 16. So we get 32.86 over 16, which is a little bit above 2. Oops. .05. And we've done some rounding, and that's okay. So what does this mean? You could say something like an IQ score of 132.86, or you could say the 98th percentile of IQ scores is 2.05 standard deviations above the mean. Okay. So 98th percentile seems really high. It is pretty high. But in terms of standard deviations, it's only a little more than 2 standard deviations above the mean. So the 98th percentile is not an unusually large, or unusually high rather, IQ score. There's nothing unusual about it in the sense of our rough rule of thumb for z-scores. It's only a little more than 2 standard deviations above the mean. Still pretty high though, but just an interesting result, I suppose. The 98th percentile seems like it would be further from the mean, but it's really not. Okay, let's do a bunch more examples. Like any of this stuff, you just have to practice it. Among all applicants to a certain university, the math SAT scores averaged 500, the standard deviation was 100, and the scores were approximately normally distributed. So the first question is, if a student gets a 350, what is their percentile? So we see that what we're measuring are math SAT scores, so that's our random variable. We see that the mean is 500. We see that the standard deviation is 100, and that this is approximately normally distributed. Okay. And again, that's because a normal distribution goes forever. Math SAT scores, at least the old one, had a maximum of 800. So it's close enough, we hope, to apply the normal distribution. So let's sketch this out and see what we're working with. So there's our distribution of math SAT scores. The mean is 500, and then we'll figure out where most of the data live. So we go up and down 3 standard deviations. So we have 600, 700, 800, 400, 300, 200. Okay. Our particular person had a score of 350. There it is. So we want to know what percentile is that. So here's our picture. So then the question is, okay, which piece do we want? Do we want to be above 350 or do we want to be below? Well, we want a percentile. And by definition, this means how much of the distribution, how much of the data are at or below this point. So we want to know this section here. How many scores, what proportion of scores are at or below 350? So we're finding a probability. Since we're finding a probability from a normal distribution, we will use the normal CDF. Okay, now here's where things get interesting. Where does this shaded region begin? It does not begin at 0. Because we're saying that this distribution follows a normal these test scores follow a normal distribution. So this goes forever towards negative infinity. So just because scores can't go below 0, that doesn't mean the normal distribution cannot go below 0. So we're actually starting at negative infinity. This shaded region starts at negative infinity. How do we enter this into the calculator? Well, we'll come back to that in just a moment. Our area of interest ends at 350.